Hello. Let's see. Okay, there's currently no one in my room right now, so I'm just gonna wait till there's like someone in here, or until it's like 9:05 to start streaming. Yeah. Hello? Okay, I'm about to start the stream in like, well, technically it's already started, but I'll officially start in like 3 minutes. Just to see if like anyone wants to like come by. James, right? How are you doing today? Taking AP Physics? It's pretty good. Okay is good. Better than bad. Yeah, this week I think we're doing equilibrium. So I'm not sure if you've been on the other physics streams. I heard they were doing Newton's first law. So they told me to make a bunch of questions for the first law. So hopefully I did that accurately. It looks like there's someone else in here. Oh, look, it's Alvin again. Hi, Alvin. James, have you been on my stream before? I have a couple questions prepared for this stream. Oh, really? Your other classmates have been on my stream? Did they say good things or bad things about my stream? Because I feel like you can tell that I'm not like a teacher. You can tell I'm a student by the way I structure things. Be honest. Classmate doesn't like. Oh, you get extra credit for going on these streams? Wow. Interesting. I did not know that. Oh, that's probably why people keep on coming to my streams. Honestly, if I were a student, I would probably get bored of my own streams. I would probably like get out of here. Like, if you're so studious to like come onto these streams like on your own, big props to you, man. Like, whoever does that, even I don't do that. Anyway, I'm gonna start streaming like the actual lesson right now. So James, I know you haven't seen me, but I'm Casey. I'm a physics streamer here. I do AP Physics, if you can't tell. Hope you know that you're on the AP Physics stream right now, but I'm currently a sophomore in university. I go to Columbia University, and I used to be a mechanical engineering major. I used to say that every single stream, but guess what? I've changed that, and I'm now an electrical engineer, but I'm still getting a mechanical engineering minor. So I still do a lot of this AP Physics stuff to for my classes. It's kind of funny because today's lesson was like covered on a recent test of mine in college. But regardless, I'm just here to like teach you guys. I took AP Physics 1 in high school before, and I did get a 5 on that. So I mean, if you need any tips or tricks on the test itself, you can ask me. I usually start the streams by asking whether or not you guys have any questions from the week. Like, I pretty much understand most of physics. I'm not gonna say all of physics because that'd be saying too much. So, like, once again, if you have any test questions, homework questions, general questions, you can ask me right now, and I can go over them on stream for free. Yeah, so I'm gonna start the content part, but if you have any questions at all, just drop it in the chat. Drop a question in the chat. Just say hey, can I know about this? Or there's this problem on my homework I don't understand. And once I finish the problem, I'll get to it. But for now, I have some pretty exciting things for this stream. Let's see. See that? Okay. We got some equilibrium today. So half of these, I usually write my own questions, but this time, according to the person that manages me, she said that some of the questions are like stuff you guys haven't covered yet, like torques, which is kind of sad because torques are pretty cool. Let's see. Oh, I don't know how to like zoom in to like, oh shucks. Okay, looks like you guys got to deal with this screen size. Let's see if I can make it a little bit nicer. Ooh. Okay, hold on a minute. Let me just adjust the size so it's not like ugly looking. Okay, I think that's good. So let's start with this problem. Okay. Car drives down a 25-degree incline at a constant rate of speed. The force of friction keeping the car from accelerating is 503 newtons. Find the weight of the car and the normal force. The tricky thing about this question is that in your head you can like imagine this situation happening, right? You got an incline and you got a car, right? You just chill in there and you just roll it, acting downwards. And yes, that is true. But if it's going at a constant speed, if it's going at the same rate, then that means all of the forces are balanced. So this would be equivalent to the car on an incline and the car completely stationary, right? And you can think about this in real life. Like if you're driving, I'm not sure if you guys drive yet. I'll be completely honest, I still don't drive, but when you press the gas and let it go, you kind of coast, right? And when you're coasting, you're not applying any additional force, but you're still in motion and you're still taking the momentum from your initial acceleration and continuing it with it. So just because you're in motion doesn't necessarily mean that there's an acceleration being applied, or I mean a force being applied. The only time you understand that a force is being applied is when it's accelerating or becoming faster than what it was before. And that's just not directly intuitive to like everyday life, but I'll continue with this content. Okay. So got a 25-degree incline. Okay, 25 degrees. And you can simulate this as this block as a car. I'm too lazy to draw it again. Okay, the force of friction keeping the car from accelerating is 503 newtons. So usually it would accelerate downwards, right? But the force of friction always counteracts the direction of motion. So it's actually going upwards 503 newtons, right? Okay. So we just gotta find if this is at equilibrium because there's no acceleration. So we can imagine this as a stationary block. And that implies that all of the forces are balanced. And currently there's a lot of forces going on here. Right? There's this downward force called the mass times gravity, which is just the weight of the block. You have normal force, right? That kind of counteracts this mass times gravity. And because like this normal force isn't quite like balances out, it has a little bit of a downwards acceleration. So you can imagine that this triangle, this line kind of extends down here, and this line kind of extends down here. You got your good old 90-degree right triangle, which is what you always want when you look at these types of questions. But I'll also go over a shortcut that I learned in college for doing these questions. So like, if you really hate drawing those triangles, you don't really need to draw them if you conceptually understand what cosine and sine mean. Okay, so I'm gonna go over the shortcut to doing this type of problem to find out whether or not this is cosine or this is sine or this is sine or this is cosine. And I'll give you a spoiler, this is sine, this is cosine. But, okay. I'll go over the trick really quick. I went over it last week, but I think it's still useful. And the way I explained it last week was kind of bad, right? So we have two situations, right? So this is where the angle theta, so this angle theta is equal to 0, and this theta is equal to 90, right? So let's say you're trying to calculate like the normal force, right? So when it's in this arrangement, the normal force is going to be equal to the weight, right? So we know that the normal force is going to be mg something theta, right? But clearly this, because mg is equal to normal force, we know that this value, okay, hold on. This value must be 1. So we know that some trig function, some trig function, if you input 0, it comes out 1. And the only function that does that is cosine. So cosine 0 is equal to 1. So normal force is equal to mg, right? This situation, this is a complete 90-degree, right? There is no normal force, and this is just going to experience straight acceleration down in the form of mg, and there is absolutely no normal force. So we know that we want to calculate normal force, and there's something here. And when you input 0, it pops out 0. And this is once again cosine. So when you want to find the normal force, you use mg cosine theta, right? And you can apply this exact same idea with this angle, right? Sine. So when you're trying to accelerate this way, when you're in this configuration, this has 0 perpendicular velocity. So this is going to be sine. And this one has like almost completely, oh, this is Newton. This is normal force. I made a mistake there, but this is completely accelerating downwards. So once again, mg sine theta. But that's a really quick crash course. It's a really nice shortcut because I feel like teachers expect you to always draw force diagrams. And that can be annoying, especially with these triangle problems, because it just gets so convoluted. Like there's just too many angles sometimes. Like just forget about the triangles and just use your brain. Like it's pretty simple, I think. Anyway, so we know that this force going this way, we know that it needs to balance out 503 newtons, right? So we need to find this that is equal to 503 newtons. And that is equal to mg sine theta, right? And that's pretty simple. You just go plug and chug. 503 newtons is equal to mass, which is, okay, I guess it's trying to find the weight. If it's trying to find the weight, we can just keep it in mass times gravity, because the weight is always in newtons. Weight is a force. Sine 25. Okay. I always use my computer calculator because my TI is dead. Okay, so 1190 newtons, 1190.19, 1190.2. And that implies that the mass is going to be about, like, it's about 20 kilograms-ish. It's a pretty light car. You know, these types of questions aren't always like super realistic. Like, if it's not accelerating at 503 newtons, you can tell that this is not a heavy car. Okay, so we got another problem here. We got a 150 kilogram light. Let's draw this. Suspended by 2 cables. One cable makes an angle of 65 degrees. Oh, I think I misordered these questions. Let's start with the easier one first. No, number 3 is easier. Okay. So a 570 Newton tightrope walker stands at the center of the tightrope so that each half of the rope makes an angle of 10 degrees. So I know that the degree sign is kind of weird here with the horizontal. What is the tension in each half of the tightrope? So let's draw this right here. In my head, this is what it looks like, right? You got your dude. He's like, hey, I'm on a tightrope. Pretty happy about it. Pretty excited. And then you have, ooh, I have colors. I should utilize it. Okay. 10 degrees with the horizontal. That implies that this guy is 10 degrees. This guy, ooh, my drawing isn't like the best. 10 degrees. Okay, let's use another color. So, what is it? This is 10. This is 10. Okay. So, in order for things to be at equilibrium, right? Oh, hold on. Let me get my colors back. So, in order for things to be at equilibrium, you need all forces in the x direction to be equal to 0 and all the forces in the y direction to be equal to 0, because otherwise it would be in motion, right? Like if it were completely still and you were to apply a force to it, of course it will start moving, and that implies it's not at equilibrium. And if you get more advanced, you also need to find that the moment, or like the torques, is also equal to 0. And that is when it's truly in equilibrium, I think. Actually, I'm not completely sure. I haven't like gotten that advanced. But we'll do moments / torques in just a moment at the very end. Okay. So we know that, okay, here's a really quick trick. Once you see that it's half of the rope, so if this person stands directly in the middle, that implies that this tension is the exact same thing as this tension, right? So let's call this tension 1, tension 2. But because they're the same, right? They experience the same amount of force. It's completely symmetric. Let's just label both of these as just tension, right? Because they're pretty much the same. Let me erase that. Give me a bigger size. Ooh, just kidding. Okay, but we know that the tensions are pretty much the same if you see a symmetrical problem. And at that point, you just immediately shortcut, because this problem is actually extremely easy to solve. But, okay, so since we know that the sums of the forces in the y direction must be 0, we have, so 0, okay, forces of y equals 0 is equal to, okay, let's try to find the force of this string in the y direction, right? So let's think about the extremes here. This is going to be sine. So tension sine theta. And there's 2 of them, right? So this is from the left side. Oh. And then plus t sine theta, right side. And then this is pulling up, but there's a 570 Newton tightrope walker in the middle weighing it down. So you get a subtraction sign minus 570, right? Because this guy is pulling it up, this guy is pulling it up, whereas this guy is pulling it down. Right? We want that to be reflected inside the signs. Or else we can't solve this at all, because like the directionality of these forces really do matter. Okay, so this is equal to 2t sine theta is equal to 570 newtons. Okay. Okay. So that's just 285 divided by sine 10. Divide by sine 10. So the tension is equal to 1641. Newtons. Right? Okay, that makes sense. Let's do a check really quick. Let me make sure that these things are right while I do it. Yeah, that sounds about right. Okay, let's go to a little bit more complex of a problem. So we have a 150 kilogram light. Suspends on 2 cables. One cable makes an angle of 65 degrees at the horizontal. Okay. Let's see. So this one's a little bit steeper, and this one's like kind of more flat-ish. You got your little traffic light. Right? 150 kilogram. That is a really heavy traffic light. One cable makes an angle of 65. Another angle, 40 degrees, right? So, okay, let's just draw the triangles here. Okay. So we got, once again, the forces in the x is equal to 0. Summation of forces in the y is equal to 0. And if you remember the last problem, I didn't need to really consider the net force in x, right? Because this person, right, does not create a force in the x direction. And if we know that this x direction is equal to that x direction, we already know it's an equilibrium, right? And I guess the only, you can't really get any information from that. You need to use a y force. But this guy is a little bit different, right? I mean, not really. I don't think you still need it, actually. So once again, we have the summation of forces in y is equal to 0, which is equal to, let's call this T1, call this T2. T1, so this is pulling upwards, right? Be very conscious of the signs. T1 sine of 65 degrees plus T2 sine of 40 degrees minus 150 kilogram. Let me. Oh, it's kind of getting to the edge over there. 150 kilogram times 9.8, right? You see, there's 2 unknowns and 1 equation, right? And that doesn't quite work out for us. So we can get another equation. So this guy's pulling this way, this guy's pulling that way. Negative T1 cosine theta, cosine 65, plus T2 sine, oh, that's not looking too hot. 40 degrees is also equal to 0 because that's the summation of the forces in the x direction. You guys, does this make sense to you guys? Like, I don't want to be confusing. If you guys are confused by anything, just stop me because I know I can get a little bit carried away at times. Okay. So, so we have T2 sine 40 is equal to T1. Oh, wait. What did I write? Why did I write sine there? That should be a cosine. Okay. T2 cosine theta, cosine 40, right, is equal to T1 cosine 65, right? And now we know that I'm gonna choose T1 because T1 is a nice even number. So I'm gonna put everything in terms of T1. Cosine 65 degrees divided by cosine 40 degrees is equal to T2. All right, so now we have a ratio and we can solve for everything in the first equation. So let's find cosine 65 divided by cosine 40. Divided by cosine 40. 0.55 is, okay, so T1 0.55 is equal to T2, right? Okay. So let me, oh, this is getting a little bit large. Okay. I'm not sure if you guys can see that, but yeah, hopefully you guys can still see the work that I'm doing. Yes. Cosine 65 divided by cosine 40. Is that right? Let me plug it in again. I'm a little bit paranoid with these questions. Like I feel like I'm doing everything right, but also wrong at the same time. Okay. So we got T1, tension of 1 is equal to 0.55 of tension 2. So F of Y is equal to 0 once again, equal to, let's plug in everything. T1, we just have regular old T1 sine 65 plus T2, which is just T1 times 0.55, because that's the ratio, times sine 40, minus, let's round 9.8210, minus 1500 newtons, right? So 1500 newtons is equal to T1 that's T1 sine 65 plus 0.55 sine 40. And you can do that really quick. Sine of 65 plus 0.55 times sine of 40, 1.26. 1500, 1.26, 1190. Okay, so T1 is equal to 1190, and once you newtons, and once you multiply that by 0.55, 1190 times 0.55, 654.5. Okay. So let's continue further. So this is starting to get into torque questions, right? And like equilibriums. Okay. So these ones you always want to draw a diagram for. Let's see how much I have left. Okay, I got 3 more. I'll spend 10 minutes on each, I guess. My friend and I are sitting on a seesaw. Right? Ooh, that's an ugly seesaw. I weigh 125 pounds and my friend weighs 150 pounds. I'm sitting 4 feet away. So let's say this is 4 feet. From the pivot point. How far away? Okay, so that means. Fun fact about these torque questions. Okay, I'm not. First off, have you guys heard of torque before? Because I don't want to like jump into something too quick before making sure you guys know what I'm talking about. Anyway, I should go over it anyway. Torque is equal to force times radius, right? And the way that I kind of think about it is that, like, if you have a really long pole arm, right? Like, once you like change a small angle of it, it has like a very large change in distance, right? Like, if let's say you have like one of those selfie sticks, right? Like if you tilt your arm up by like 10 degrees, it can like have this like huge difference in distance, right? And the other way can go like it can go the other way, right? You can have like you can use a lot of force and move it like a little bit of force and move it a long ways, and you can move something that has a lot of force but a small distance, right? It's kind of this like balance of like forces and radii, right? So another way to describe torque is by the moment, right? And you got a pivot point, right? So fun fact about pivot points, you don't really need to care about forces directed towards the pivot point. But you can imagine that even if all the net forces of y is equal to 0, so that's the initial condition of equilibrium we started out with here, right? Even if all the equilibrium forces in y is 0, does not necessarily mean equilibrium. Right? It could equal equilibrium in certain situations, but not all, right? So let's say that I have my, I don't know, 150-pound friend here, and there's an upwards force of 275 pounds exerted by this pivot, right? Because force in y direction is 0. But if you were to hold this constant, you would see that, oh, just realized I put it in equilibrium by accident. I mean, you can apply the 275 force here, and you would see that this would start rotating in like this direction, right? It does not necessarily mean it's at equilibrium, even though all the forces together is 0. Okay, so that's saying that if this upwards force is here. So the way that you take torques is that you have a pivot moment, right? Not pivot moment, like a pivot location, and you calculate all of the forces in that direction. So let's say that the moment in y, let's say that this direction is positive, right? Is equal to 0, because that implies that it's not spinning. And if things are spinning, you definitely know it's not in equilibrium. And you want things to be in equilibrium in these statics problems. So in the moment, oh, why did I put y? The moment at the pivot point, moment at P is equal to 0 is equal to, so we know that this is going down, so this is pushing it clockwise, right? Is equal to 125 pounds times radius, 4 feet. And you might be noticing something weird. I'm using these customary, like imperial units or whatever, and you're like, wait, but we don't use those in physics. And let me tell you, in these torque questions, it doesn't matter because it all balances out, right? Because these torque problems are mostly about the ratio of the distance and the mass. And as long as you maintain that ratio, it should be fine. Like your result will obviously be in pounds, but it doesn't really matter. It's still going to work out. It's not like kinetic energy where you don't really have, I actually don't know, but you don't have a unit for energy inside other unit systems. But let's continue. So this guy is pushing you clockwise, right? And we define clockwise as positive. But this guy, if you imagine that from this pivot point, right, let's hold this point, like let's have this point stable, but you push it down here. This entire thing starts rotating counterclockwise, right? And if it's rotating counterclockwise, we define that as negative. So minus 150 pounds. And then this, we're trying to find the distance, right? Times distance. Okay, so we can just do some basic math. 500 is equal to 150 distance, and distance is equal to 500 over 150, which is, I don't want to pull up my calculator. 10 over 3, right? 3 1/3, 3.3333. Yes. Okay, so this distance is 3.33 feet. Okay. That's pretty good. Let's see. I'm sitting with a different friend. Okay. See if there's anything else I want to cover here. That's basically it. I'm sitting with a different friend. I once again weigh 125 pounds, but this time I sit 6 feet away. Let's see. Let's get my brush out. Let's draw this. Ooh, I'm really bad at drawing these seesaws. Okay, got a pivot point. That looks like a Subway sandwich. I don't like that at all, but I'll keep to it. I weigh 125 pounds. All right, and I'm sitting over here, 6 feet away. My friend sits 5 feet away. Got my buddy here. All right, and we want to know how much does my friend weigh. Okay, so we got the center pivot point. Then we have, let's take this moment. Calculus is positive moment. But the point, say this is positive, is equal to 0, is equal to, okay, this guy is pushing down, 125 libs times 6 feet. Let's see. Oh, it's getting tight again. I wrote this way too big. I did not need to write it that big. Okay, I wrote that a little bit smaller. And then we got this guy also pointing down, but if you imagine him pushing down here, this guy starts rotating the other way, counterclockwise. So it's negative minus his weight times 5 feet. Right? This is pretty simple. That means 125 times 6 is equal to 5 times weight. 125 divided by 5 is 25 times 6 is equal to weight. Now it's going to be 150 pounds. Yes. Was he 150 pounds in the last one? Gosh darn it. Yeah, he was. Okay. Let's go to the next one. The next one is a little bit more conceptual, right? And I kind of designed it to be that way. I have a massless bar that is 1 meter long. Okay, let's draw this bar. I'll use a triangle tool this time. Okay. Ooh, stop that. So I have a massless bar, and that's gonna be a key word right now. Massless, right? And gravity only affects things that have mass, right? Like if you think about the force of gravity, mass times gravity, if there is mass 0, then the force of gravity is 0. Okay, so basically this guy, you can kind of imagine is in space, right? I exert a 20 Newton force on one end of the bar. I exert another force the same direction and magnitude as my first force, but on the other end of the bar, right? What will happen? So that implies that I have another 20 Newton force being applied here, right? Now let's take the moment about this point. Let's say that you take, let's say the point is here, right? Let's calculate the moment, okay. So that implies that this is 0.5. 0.5. Right? Moment, let's see if this is indeed, in fact, in equilibrium in terms of moment, right? So moment about the point in the positive direction is clockwise. Okay, so if you imagine this pushing it, it would go counterclockwise, right? So 0.5 meters times 20 newtons. Okay, so you got this other guy. If you were to imagine only this guy pushing, this is trying to push it clockwise. Oh, I forgot to put the negative here. So this is going to be plus 0.5 times 20 newtons. Okay, so when you do 0.5 times 20 minus 0.5 times 20, that's going to equal 0. So yes, indeed, it is in equilibrium. And concern with the moment. But if you think about this bar in terms of the net force, okay, we can also talk about net force in the x direction, right? It's equal to 0, and there's nothing moving this left or right. So net force, the x direction is 0, but you have the net force in the y direction, right? And that's equal to this 20 Newton force plus this 20 Newton force, right? So 20 newtons plus 20 newtons is equal to 40 newtons, right? If you want to be at equilibrium, because at equilibrium, the summation of forces in y direction should be 0, right? And you'd be like, wow, that's weird, because when I think about like when I have like this pencil, right? Like I'm putting like the same force up here and up here at the same time, right? And you're like, wow, but this is at equilibrium. And something that you need to consider is that there is another mass that is pulling this guy downwards, and that's mass times gravity. So in this situation, if this pen were massless and I were to apply the same amount of force as I am right now to a massless pen, this guy would be accelerating upwards. But because of the way that gravity works, that the normal force automatically reaches equilibrium with whatever force I'm applying to it. Okay, so in this situation, so in the situation in part A, what was it? Forces in y, not in equilibrium, but the moment is at equilibrium, right? This time, we have a different situation over here. Okay. I drew this all way too big. I like drawing things very large. That's the situation over here. Let's draw another situation. Okay. So we have this time I exert a force in the opposite direction, but with the same magnitude at the other end of the bar. So I still exert a 20 Newton force here, but I exert a downwards 20 Newtons here, right? And this guy is completely massless. And this is very intuitive with like the real world, right? Like if you imagine that I have this pen and I exert upwards force here, exert downwards force here, it's not equilibrium, right? So this is something that's more reflective in real life. And even if you were to have mass in this pen, it would still accelerate downwards. But let me just demonstrate why. Okay, so in this situation, you got the summation of forces in the y direction is equal to 0. It's just equal to positive 20 on the right-hand side, minus 20 newtons on the left-hand side because it's a downward force. And you do have equilibrium in terms of y forces, right? So this is an equilibrium. Check mark. But you also have a moment, right? Let's take the moment about here. And it really doesn't matter where you take the moment. If you take the moment about here, take the moment about here, take the moment about here, it doesn't matter where you take the moment because it's ultimately going to be the same, right? Okay. So, okay, I shouldn't say that the moment is the same in all aspects. The moment is only the same at equilibrium. So that's probably something I should say carefully. But let's say that you put it in the middle, right? Moment about point, positive direction, right? Is equal to, I shouldn't say 0 quite yet, but you say that clockwise is a positive direction, but this is going opposing that. So 20 newtons times 0.5, right? Minus 20 newtons is opposing it. And you can imagine this guy, he's also going counterclockwise. So both of these guys are pushing this rod to go into counterclockwise rotation. And that is definitely not an equilibrium, right? So you got minus 20 newtons times 0.5 meters. Okay, and then you see that this is indeed a moment of 20 newtons, negative 20 newtons, in fact. And that is not an equilibrium. Okay. So we can extract a lot of information from this idea, right? So in these situations, we have two forces acting on a rod, but they're like, no matter how I point it, if I point them in the same direction or point them in opposite directions, like it's still not in equilibrium, right? And you can kind of extract that no matter how you angle it, unless they're pointed together, like not like pointing in the same direction, like they're directly pointing together, as in they're causing like a tension or like what was it, a compression of a sort, which I'm pretty sure is somewhat irrelevant right now, but like as long as you have two forces acting on a rod, there will never be an equilibrium, other than that one case where they're pointing in the same direction, right? So you can kind of see it in these situations. Like on this other end, like as long as I point in any direction, there's still going to be some sort of moment. And if there's not a moment, it's complemented by the force in the y direction, right? So it doesn't really matter what you do in this situation. It is physically impossible to reach an equilibrium with only two forces acting on a bar. And that's just a fact of life. And we just like demonstrated that right here. Okay. So that's pretty much all I have for this week. It's pretty simple. I have more questions. Okay. Let's see. Okay. Do you guys have any questions from your homework or anything? You guys want me to talk about anything? I can pull up more questions that I wrote for backup if you want. So if you guys don't have any questions, I'm just going to do even more problems and mostly about, what was it? Mostly about equilibrium. Let's see. I'm pulling them up right now. If you guys are interested. Okay, let's do this problem. We got Got 9 more minutes, and I kind of enjoy torque problems. I'm not even sure if you guys had torque problems before, but let's see. Just a moment. Snipping tool. Oof. I feel like these equilibrium static problems, according to like other mechanical engineers I've talked to, they find it very boring because like nothing's moving. And so for some reason, mechanical engineers kind of like it when things move, apparently. And I feel like when things start moving, it's kind of scary. Like not all things add up to 0, and there's not like any sort of like thing you converge to. I find that a little bit terrifying personally, but I guess a lot of other mechanical engineers find it exciting. Okay, I got another problem. Let's see. It's another one of those good old seesaw problems. Let's share my application window. And we got 8 more minutes. Let's see if we can do this. Okay. Brush. I'm still on the seesaw, and I still weigh 125 pounds. Right? Just draw another seesaw. I've discovered this rectangle tool, very helpful. And I also just now discovered this triangle tool, which I will use to my advantage. Okay. Oof. Adding little black dots everywhere. Okay. Let's move this guy down here. I'm still on a seesaw and I still weigh 125 pounds. I brought 2 friends over. One weighs 120 and one weighs 150. I'm sitting 6 feet away from the pivot. I'm sitting 6 feet away and my 150. This is me. Oh, wait. I weigh. That's not 160 feet. That's 6 feet. Okay, 6 feet away, and I'm just chilling here, hanging out on my seesaw, and I weigh 125 pounds, right? But my buddy here, my buddy who weighs 150 pounds, sits 3 feet away. I got my other buddy. He's a little bit chunkier than me, but it's okay. I still love him. He's 150. So I got a third buddy. He wants to join in all the fun that we are having right now. And he's like, where do I sit to maintain this static equilibrium? And you gotta be like, okay, then let's calculate the torque. So let me just extend this. I keep on drawing too big and I keep on getting punished for it. And like I still do the exact same mistake. Okay. So my buddy weighs, what was it? 120 pounds. Right? We're taking this pivot point. Call this point P. Okay, let's take this moment. Moment P, positive direction, is equal to 0, which is equal to 125 times 6. Oof. Why do I keep on writing so gosh darn big? I'm like making a fool of myself right now. Okay. 125 times 6. So that is pushing in the clockwise direction. This guy, when he's chilling, it goes down. It's pushing the counterclockwise direction. Minus 3 times 150. And we don't know whether or not he's going clockwise or counterclockwise, right? So let's just assume positive, right? Because if he does end up sitting on this side, the x direction will end up being negative. So let's say positive distance times, what was it? How much did he weigh? My buddy weighed 120. Okay. So I don't know whether or not he's going to sit on this side or that side, and that's why we got to check the torques, right? So 125 times 6 is 750? Yeah, 750. Is it 750? Yeah, it's 750. Mine is 450 plus distance times 120 is equal to 0. And you got 300 is equal to D120. 300, negative D120. Sorry, you gotta be very careful with the negatives in these situations. 120 equal to D. And D is equal to 30 over 12. It's equal to, I don't want to big brain this. I'm just gonna 2.5. Feet. Okay. I think that's all I can do this week. My battery is actually about to die on my laptop that I'm streaming from, but anyway, I hope that was helpful for you guys. Come back next week with questions and problems. Yeah, you guys have fun. Hey, I'm gonna end the broadcast here if that's okay. So, later. Bye.